I'm super excited to be here, and it's such an honor to be speaking on a roster of so many incredible other speakers. I was looking at the other speakers and all the things that they've done, the research they've done, what they've contributed to functional programming, and these really impressive credentials and great degrees from big universities. And just so you know, I also have an advanced degree, so that's why I'm qualified to be here speaking to you today. I have a master's degree in opera, actually. That was my sort of first career. I started programming as a kid and took a 10-year break to do the music thing, and then went back to programming. And I've actually been writing Elixir now for 2 years. That's my functional language of choice. And what I'm going to talk to you a little bit about today is the examples are in Elixir, but it applies to any language where you have a module. So I assume that's many of you all. So this is my dog. She's much bigger now. Her name's Miki. She's about 4. This is her right after we got her. She still loves to lick my beard, which is very cute. But I walk with Miki every morning and every evening, about 45 minutes through the park in Berlin. And while I'm walking, I'm usually listening to podcasts. And one night, I was listening to this episode. So this is a podcast called Undiscovered. It comes from American Public Media back in the States, and it's focused on issues of science and math and the stories behind science and math. It's a great podcast. I really recommend it. There are only a few episodes. They're going to make more. But this episode in particular was about this phenomenon called the 6 degrees of separation. The idea is that we are all connected. Every person in the world is connected to every other person in the world in less than 6 handshakes, 6 or less handshakes. You may have also heard this in another iteration. So there's this game called 6 Degrees of Kevin Bacon that says you can connect Kevin Bacon to any other actor, living or dead, in less than 6 degrees based on just who's been in what with someone else. So the idea that these networks exist had been around for a little while. There's actually some initial research back in the 50s by a researcher named Stanley Milgram, who you may know from a very different type of experiment. But the episode of this podcast focused more on the research of these 2 men. So that's Duncan Watts and Stephen Strogatz. And back in 1995, Duncan Watts was a researcher studying crickets in the basement of Cornell University in upstate New York. He was actually a mathematician, so why he was studying crickets, I still don't really know. But one night when he was sitting in the basement of Cornell, listening to crickets chirp, he was thinking about something that someone had told him earlier, which was this idea of 6 degrees of separation. And being a mathematician, he thought that sounded like a really interesting math problem. So he pitched the idea to his advisor, Dr. Strogatz there, and they said, sure, let's dig into it. Let's see if this is even possible. So what they did is they started off with the 2 known types of networks at the time. There was this idea of a regular network, something that has has structure and format to it. This particular network is called a lattice network. And just so you know, being not a mathematician, I am going to use the terms network and graph somewhat interchangeably here, even though they are technically different, but that's just me. So yeah, this is a lattice network, and these networks have a characteristic. 2 very important characteristics. One is that they have what's called a very high clustering coefficient, and then the other is that they have a very high mean shortest path. Now, if you're not familiar with those terms, that's okay. We're going to go into them and explain what they are. But these regular networks are characterized by those 2 things. And then there was also another kind of network that they were familiar with, and that was the random network. Now, this example, this random network, has the same number of nodes, same number of edges, but those edges are assigned, those connections are assigned completely randomly, according to just random assignment. And these random networks had a very different set of attributes. These random networks have a very low clustering coefficient, but also a very low mean shortest path. What they discovered was that if the world were a regular network, then this whole idea of 6 degrees of separation cannot possibly be true. There's no way that every other person can be connected in 6 degrees because of that very high mean shortest path. But if the world were a random network, well, yeah, I mean, we don't even need 6 steps. You only need 4 or 5 to connect all 7 billion people on the planet, assuming they have a sufficiently high number of connections. And the real breakthrough that they had was realizing that this isn't how the world, is certainly not the world of people's interpersonal connections, is structured. We have cliques. We have people that we're all related to, family that all knows each other. There's a lot of connectivity within those groups, and friends and coworkers. So our connections are not random. They are very regular. But how could it be possible to have this 6 degrees of separation with essentially a regular network structure? And what they realized was this. If you take a regular network and you change just a couple of those connections, very quickly you get a very low mean average path. So what we have in these small world networks, which was the term that they coined, is a network that has a very high clustering coefficient but a very low mean average path. You sort of get the best of both worlds from both of the other existing network topologies. So now I think it's kind of important that we learn how to calculate these two metrics, this clustering coefficient and mean shortest path. So this is the formula that they gave in the paper that they published in the journal Nature in 1998. That's how you calculate the clustering coefficient for a given node in a graph. And then the clustering coefficient for an entire graph is the average of those two nodes, of all the nodes in the graph. So everybody understands what this means, right? If you're anything like me, that makes no sense to you. Like, again, musician. And there's a joke that you hear in conservatories sometimes that there are 3 types of musicians, those that are good at math and those that aren't. So we're going to go and actually talk about, in normal terms, how we calculate this clustering coefficient. So first, you need to get the clustering coefficients for a single node. And for that single node, you need to say, how many neighbors do I have? How many other connections do I have? And then of those connections, how many possible connections are there between my neighbors? And then of those possible connections, how many of them are actually there in the network? How many connections are there? And then that is your clustering coefficient. It's the number of your actual connection over the number of possible connections. All clustering coefficients, 0 is no clustering, and 1 is very high clustering. So let's look at an example. Let's imagine that we have these 4 nodes, and that blue one is the one we're going to be calculating our clustering coefficient for. And we start, it has 3 connections to those 3 other nodes, and if all 3 of those connections were there, then we would say that that node has a clustering coefficient of 1. All 3 of the 3 possible connections are present. But if only 2 of those 3, if that middle one is not present, then we say that that node has a clustering coefficient of 0.6 repeating. Okay? And on down the line, down to 0.3 and 0. Then, to calculate the clustering coefficient for an entire network or for an entire graph, you go around the circle, basically, in this case, and we say the clustering coefficient there is 2 out of 3, and here 2 out of 3 as well. This bottom one only has 2 neighbors, and there's 1 connection that's present, and same thing over there. So we can do a little bit of math and find out that the average for the entire network is 2.5 over 3, or 0.83 repeating. Now that's considered a fairly high clustering coefficient, and from looking at this graph, we can see that there's a lot of connection there. It's a very cliquish graph. Almost everybody knows almost everybody else there. And then the other term we were talking about earlier was the average shortest path, or the mean shortest path. And this one's actually, luckily, quite a bit easier. So in a network or in a graph, to calculate the average shortest path, you take all possible pairs of nodes, and then you use some algorithm to find the shortest distance between those nodes, and then you take the average of all of your possible pairs. Luckily, that shortest path length is a very solved problem in computer science. It's very efficient. There are lots of things that can do it for you. So this quote comes from the paper that Strogatz and Watts published in '98. These things, when I was reading this paper, sounded really interesting. Sounded like something I want to have in my software. I want to have enhanced signal propagation speed. I definitely want to enhance computational power. And synchronizability sounds cool too. I was thinking that maybe this would be something that would be great in some sort of distributed calculation, so like a MapReduce thing, or some sort of machine learning or big data stuff. Also, the synchronizability would be great in an eventually consistent database like REAC. So I was curious if these things actually existed, and I continued reading the paper. And luckily, they had to have proof for their assertion as well. They had this idea of a small world network, but they needed to actually find them. So the first place they looked was here. That's a little worm called C. elegans. C. elegans is great for research because it has about 208 neurons in what you might call its brain. And you can slide one of these things under a microscope, and you can look and see all of those neurons, and you can see how all of them are connected. And lucky enough for Duncan Watts, that information of how all those neurons were connected was sitting there on a floppy disk at Cornell, and he could look at it and assess that network and see that those neurons are all connected in a small world network. And it would make sense then that if brains of nematodes are connected in a small world network, that actual neural networks are connected as well. Many neural network implementations are small world networks. I can't speak as to whether that is intentional or not, but that is something that you find. Many neural networks these days are small world networks in how they're designed. They also looked at the power grid of the Western United States. Now that's something that you really want these properties of a mean shortest path, because you don't want electricity traveling too far, otherwise it loses a little bit of its power, but you also want reliability. You want clustering so that if something goes down, you can get it from a different way. So funny enough, even though at the time no one had come up with this idea of a small world network, that just happened to be there. It was designed in that way naturally. At the time, their paper was published in 1998, Facebook didn't exist, but later on, after it did exist, and they had a little over 1 billion users, they did some research as well and found that the connections in their social graph are, of course, a small world network. And they even saw that you didn't need six handshakes. You only needed a little bit between 4 and 5 to connect most people. People have even seen small world networks in the relationships between characters in Game of Thrones and in natural language, in human language that has existed well before we even had an idea of what networks and computer science were. So these networks are everywhere. There's a phenomena that you can see just about everywhere in the natural and man-made world. But that last bit is what really interested me, because I wanted to know if these are in our software, these small world networks, if we can find them in our software. And more importantly, I wanted to know if we could find them in our code. I'm really fascinated by how we create new abstractions and how we organize code into human understandable concepts. And I wanted to see if maybe these small world networks could help us organize code better so that we can leverage some of this power to better maintain and organize our code. So what I did is I wrote a little tool that could parse Elixir and see what modules depended on other modules. So, and just so you know, what I'm calling a dependency is anytime one module calls a function in another module, or calls a macro in another module, or includes that module, because at that point you don't know where exactly the function's coming from. But if we assume that it's including it or some function from it, that's a dependency. And what I got, what I wanted is to see a nice graph so that I could see all of those dependencies. And I got that. It was great. This is the dependency graph for a library called Benchee. It's a benchmarking library in Elixir that I work on with my friend Toby down there. And this was like almost everything I wanted. It's a little blurry here, but you can see the idea is pretty clear. You can see what modules are using what other modules. And that's basically what I wanted. But I pretty quickly ran into another problem. So when you started getting with bigger libraries, they started getting pretty hard to use. So this is the dependency graph for the Phoenix application that serves the website for thechangelog.com. That's another podcast I listen to sometimes about open source. It's really wonderful, but they serve their website from a Phoenix application, and it's huge. And there was no way I would be able to look at that graph and get any usable knowledge as a human. I needed a better solution. So I found this. Luckily, it's called Gephi or Jeffy. I'm not entirely sure how to pronounce it, but it's an open source Java application that runs anywhere, thanks to the JVM. Thank you for that, guys. And it was everything I needed. It gave me a much better interface to work with these larger graphs, but it also gave me calculation of those two metrics that we had spoken about, the clustering coefficient and the mean shortest path. So I got to playing, and I put some stuff into Gephi. Now what I did is I started with 14 applications. Of these applications, 5 of them were Phoenix web apps, so pretty large, and 9 of them were smaller open source libraries. Why 14 applications, you ask? Because I am not a real scientist. After 10, I saw a pattern, and then I did another 4 more, and the pattern was still there. And to me, I felt that was kind of good enough. I also have 2 little kids that I like spending time with, so I didn't want to spend all my time analyzing all these libraries. I felt I had something that was pretty cool. But I also do want to say that this is not a substitution for actual peer-reviewed research. I would love if someone would dig into this more who had the time and the resources to really explore this in depth. I do think that there's something there, but I just want to give that caveat that musician, not scientist. So what I got were graphs like this. This is the dependency graph for the modules in the web application that serves hex.pm. So this is the package manager for Elixir and increasingly for Erlang as well. And their web application is a Phoenix app as well. And I could get really great, pretty graphs like this thanks to Gephi. And I could also do fun stuff like this. I could color the nodes based on attributes of those nodes. So in this case, this is the dependency graph for Benchee again. And the darker green ones have the higher clustering coefficient, and the lighter green ones have the lower clustering coefficient. You could even dig into the specifics on each node. They have a really great breakdown where you can see the attributes of every node in your system and see how they relate. I spent, frankly, too much time doing this because it was really cool and making pretty graphs and stuff. But I needed to get back to the original question, which is, are there small world networks in these graphs, in these networks? So I took a look. As we can see, not really. That's the clustering coefficient, and this is for hex.pm again. It's a clustering coefficient of 0.214. That's really low. 0.10. That's really low. And I also noticed this, which you definitely can't see, but up there, there's a very tiny red dot that shows that of the almost 350 modules in this application, more than 250 of them have a clustering coefficient of 0. No clustering whatsoever for more than 2/3 of the application. That was weird. But I kept going. I thought maybe this is an outlier. And then I saw this. So this is Plug, another open source library. Clustering coefficient 0.21. And then this is Postgres, the Postgres driver. Again, very small, 0.20. Timex, another open source library, very small, 0.33. This was actually the biggest I could find. Distillery, very small again, 0.31. And lastly, Xdoc, 0.31. So, oh no, not lastly, we also had the changelog as well, that big Phoenix application I showed you. That's 0.2. So at this point, I already know small world network not found. I thought that would be there. I really did, but it wasn't. And just to take it that next step, because there are these two attributes, it's the clustering coefficient and the mean shortest path. I looked at the mean shortest path and found that they were all very small. These networks were showing indications that they were random networks, which I frankly couldn't believe. There's no way that we create modules randomly, that there's no structure or there's no reason behind how we create abstractions in Elixir applications. I just couldn't believe that. So I had to think some more. I refused to admit that it was possible that there's no rhyme or reason to how we create abstractions, because that clearly wouldn't make sense. And eventually, I walked my dog some more and I thought some more, and it came to me that what we have is something that we deal with all the time that has a very low clustering coefficient and is very efficient to traverse, and that's a tree. And then it made total sense, because when you're trying to solve a problem, you start with essentially that problem. You say, I want to do a thing, so I'll write a function to do that thing. For example, I want to write a function that can benchmark Elixir functions and tell me how fast they are. Maybe compare them amongst each other. And so you write one function that does all of that. And because that is just madness in trying to maintain and work with, maybe you split that up into multiple functions. So now we're breaking things down a little bit. And at this point, we have a bunch of functions, but those functions are still really big. So maybe you break those functions up a little bit more. And now we have smaller functions, but we still have that one huge module with like 150 functions in it. That's not easy to work with. So now we group some of those functions together into modules. And what we've done is we've taken that problem and we've decomposed it into its individual parts, and we've grouped those together. We've created logical abstractions that make it easy for us to know what part of the problem we're working on. And what we've ended up with is essentially a tree. We have that one problem that we're trying to solve, and to solve that, we've broken it down into smaller subproblems. It's like the basis of computing, is decomposition. And maybe it's not just a tree. Maybe it's a little bit more, because maybe there's some shared code that you want to extract. There's some duplication. And when you do that, you end up with this sort of structure. It's almost a diamond shape. But you still have very clear levels of abstraction. And you still have really unique structure that makes total sense, but it also has a clustering coefficient of 0. This graph has a clustering coefficient of 0, so it is not a small world network. I actually found this somewhat frequently in the wild when I was looking at those libraries. This is the module dependency graph for an HTTP library in Elixir called HTT Poison, which is very clearly a very wide tree. They did just that. They broke down that one problem that they had into several smaller problems, and they ended up with something that had very, very low clustering. But I thought back, and I had another question now, which is, where is this clustering coming from? If we're going to be breaking down problems into essentially these tree structures with almost no clustering, how are we seeing some libraries with a clustering coefficient of like 0.33? And these are libraries written by programmers that I admire and respect, and I would imagine that they're doing a good job. So there must be some reason for this clustering. And what I found were two more patterns. So we go back to this idea of some shared code that we've extracted, maybe a little helper module which has some functions in it that's used in a bunch of other modules. Well, right now this has no clustering. But if we add one more connection, now there's a significant amount of clustering in that application, just by having that dependency that goes down an extra level. Now, I wouldn't say this is really a problem. You're going to see this quite frequently. You know, enum is going to be used everywhere. String is going to be used very, very frequently across many different levels of abstraction. I wouldn't think that you would necessarily need to solve this as a problem. I don't see this as a problem. But there was one other case that I did see that was a problem, that I thought was a problem. So what if we need to add a logger to Benchee, that instead of formatting and writing to the console, you're writing to a log file as well. And in that logger, it's depending on some functions in the console formatter, because they're basically just taking raw data and formatting it in some nice way, and instead of writing it to the console, they're writing it to a log file. So you depend on those functions in the console formatter. But as someone maybe coming into that code base later, you might ask yourself, why does the logger depend on the console formatter? Why am I calling those functions? That doesn't seem like a very clean abstraction to me. This is an instance that I saw of when maybe there's a missing abstraction. Clustering was an indicator of something that can be abstracted, an extra concept or idea that can be named that can improve the readability and the understandability of that code to people coming into the code base later. So while this is fine and this works, and maybe if it's just one function, it's not a big problem, but maybe if it's several, it might be better to extract those functions out into another module that's depended on by both of those other modules. This, to me, is nice and clean, pretty simple, makes sense, but it also has a clustering coefficient of 0. So we're back to that idea of removing clustering. Now, before I came to Elixir, I spent a lot of time in the object-oriented world, and in that world, there's this idea of a code smell. A code smell means that not necessarily that something is wrong, but maybe something might be ready for improvement, we'll say. And to me, I'm starting to see this idea of clustering as a code smell. It might mean that maybe there's an abstraction there that you can make. Maybe there's another concept that you can name to help you reason about your code better. It's not always there, as we showed in that original problem with some of those very basic abstractions where we pull something out into a very, very widely used module. But in other cases, it might be helpful. So that's the thing that I really took away from this exploration, is seeing where clustering is, how it can be affected, what it comes from, and how we can use it to potentially write more understandable software. So this quote comes from the last paragraph in Watson-Strogatz's paper. And I definitely think that they are right. These small world networks and these small world architectures have such a unique property that they are found everywhere. And it really does warrant more research. And I would hope that this continues to be explored in our world, the world of computer science. From what I could find, there was very, very little exploring these types of ideas. Usually they were on the actual topologies of relationships between a running program and not in the code itself, and how that code might be structured better, and the relationships between parts of code, be it functions or modules. So I would love to see people dig into that more, the people that actually are scientists and have the resources and the time to explore ideas like this. And as I was working on this idea and exploring it more, I thought thought of a few other ideas that I just want to toss out there in case anybody knows anybody. I know there are a lot of very smart researchers here at this conference, so maybe I can convince somebody to dig into this more, because I do think it's really interesting. One idea I thought of is maybe there is some relationship between types in a typed language. I don't work in any typed languages. I have no idea. Maybe it's a thing, maybe it's not, but maybe if you look into it, there could be something there that could help you design your applications better. This is something that I actually really wanted to explore but couldn't get a hold of the data. So I would be shocked if in large-scale OTP applications, the message sending between processes wasn't a small world network, especially in those processes or those applications that are modeling human conversational patterns, things like WhatsApp, you know. But I would love to see how large-scale OTP applications, the relationships between processes in those applications, how they're sending messages, how they're interacting, what depends on what communicates with what the most, and to see if there is small world network there, or if there isn't, could we improve by making it a small world network? Similarly, relationships between services and a microservice architecture. Now that those are becoming larger, if people have the data, they might find something there. But those attributes of small world networks, that consistency, the synchronizability, the computing power, I would imagine that you might want that in your microservices architecture. Also, consensus-seeking algorithms in distributed systems, again, about that synchronizability thing. If small world networks aren't being used for consensus-seeking algorithms, maybe we could design a better consensus-seeking algorithm by consciously designing a small world network. I don't know. Maybe that's the way it already is. But if it isn't, that would be interesting to know. And lastly, I sort of intended this as a bit of a troll, because I'm like vehemently allergic to hype, and everybody's talking about blockchain and Bitcoin and stuff. But I would actually be shocked if there wasn't a small world network hiding somewhere in some blockchain application. So if you do want to get on the hype train, please check it out. So that's all I have for you today. Thank you very much for having me.
Thank you for a great presentation, and it was very interesting, but I have one question which I didn't understood, and it is that you were I could see the benefits in in between the people when there is a small world network, but you were speaking also that we can improve, for example, the messaging patterns in OTP application by making it a small world network. So why do you think that this is an improvement from, for example, the tree? Because the module system of an application was not a small world network. So what are the benefits for in this programming world?
Well, when we look at the characteristics of a tree, which is essentially a random graph, the clustering in that, the lack of clustering in that, means that it is slightly more difficult outside of normal cases to communicate between processes. So there might be extra steps in highly cliquish processes. So I would imagine that, for example, if you have a process that represents for example, if you are WhatsApp and you have a process that represents a person trying to communicate with another person, if you have a large sort of tree structure of a lookup to get to from one person to another, that will take longer than if you need to have some sort of clickishness, some clustering within that smaller part of the network. So if you add basically horizontal connections in a tree, you bring down the shortest path by increasing the clustering within that small thing. So I would imagine that that's that increased synchronizability that they mentioned that small world networks have. So I would assume that that would help you basically get two states that need to be synchronized faster. So if you have an inbox for one person and an inbox for another, and you're trying to make sure that they both have the same set of messages that represent the messages that they've sent to each other, and you need to synchronize those, then a small world network would give you increased synchronizability. So that would be my assumption, but I don't know. It could already be that in those large-scale OTP applications, that's already there. I just don't know of any research that's shown it, yes or no, either way. But then there are definitely things like, one of the things I thought of was maybe supervision trees, but it was no, clearly that's not a small world network, that's a tree. It says it in the name. And that's something that that you don't necessarily want to have as a small world network unless you're doing like one for all. So essentially all of your child processes are connected, because if one crashes, it's going to propagate down and restart the rest of them. So, but yeah, clearly the way that's set up is a tree, and that's set up for a very specific use case, and I don't think it can be improved, but it doesn't mean that there aren't possible ways that we could explore and see what's there.
Okay, there's one question here.
Actually, I have a couple of questions. First thing, you wanted to mention something about the statistics that you made, about the point which was high above. Mm-hmm. Is that the kernel module or something else?
So those, that was a histogram of the number of modules, the number of nodes that have a certain clustering coefficient. So that one point way at the top showed that there were, for example, of that hex PM, there were about 250 modules that had a clustering individual modules that had a clustering coefficient of 0. That was a huge outlier in terms of the distribution of clustering coefficients across that graph. So it's not necessarily that one module was being used everywhere. That wasn't a measure of connections. That was a measure of the clustering coefficient of modules, a histogram of that. So most modules in almost all of these applications had a clustering coefficient of 0.
Okay, and the second question. While you were talking, I was also thinking about this. The thing is that how Erlang solves the process management and everything, it's very similar to how the computer works. Actually, it starts from one point and it's a tree the whole way. Yeah. And the thing is how they accomplish, the same as the computer, they have registries when they have only hashes and dictionaries with addresses and stuff like that. Maybe this is for another kind of architecture. Maybe it's an architectural another approach totally, not this one. I don't know about quantum stuff, maybe that. You're a musician, I'm a software engineer, but not that much. And have you tried that? Have you seen those stuff? Because
yeah, so like I said, I don't think that everything has to be a small world network. They're not going to be necessarily everywhere. But because they are a unique network topology that I think not many people are aware of, and that there are sort of observationally proven benefits to that network topology, I think it behooves us to at least explore the idea. There could be constraints, like just the fact of how computers work, that means we cannot implement a small world network. But if there are other ways that we can leverage that network topology, because as programmers, I know I think of everything as a tree or a list, basically, and a list is basically a tree. Like everything is a tree, but maybe everything shouldn't be a tree. Maybe there are things that we can improve by using other structures and other ways of designing an application, both at the code level and at the runtime level, that could give us some benefits. So if we, I definitely think it's something that is worth exploring, but it doesn't mean that there's absolutely something there.
Okay.
Yeah.
Yeah, I just have a comment. Mm-hmm. I think the module structure as a tree is really good. So, and the separation of concerns. For me to understand the network, it's better that it's not the connected network. Yeah. So the only reason is for speed. So it's an optimization thing. Some places we probably will benefit from having a connectedness.
Yeah,
but that will cost understanding of the network. Mm-hmm. So it's just for the speed, and that's an optimization thing, I think.
Oh yeah, absolutely. Yeah. I mean, like I said, a code smell doesn't necessarily mean that something is wrong. And often when you need to make those sorts of trade-offs, it's a trade-off you have to make. It's a trade-off that everyone makes. That's usually the trade-off that people make most when they're designing an application, is speed for complexity. So that's a totally valid thing to do. That's something that we all have to think about, and that's why they pay us the big bucks, is because we're the people that can make those tough decisions. But that's absolutely something that frequently has to be done, is that trade-off of speed for complexity.
Building on that, isn't it the case that it's actually not beneficial for like a module architecture to be a small world network?
Yeah, so I think that's what I noticed, is that my original theory upon hearing it was that it would be a small world network, but after doing the research I found that it's not, and that it is in fact not beneficial. Okay. Like we can use the measure of that clustering to see where there are potential things that we might fix. So clustering I'm actually seeing as a code smell, essentially, not as a beneficial in terms of how we structure the dependencies between modules, how we decompose our problems, basically. If we're decomposing a problem cleanly and making good abstractions, we should see a very low clustering. There are cases, like I showed, with maybe there is some, like the enum module in Elixir is going to be used everywhere, but and the string module, but in our applications, we should potentially aim for a tree, for something that is not a small world network. But I could only arrive at that by trying to find the small world network, and then it sort of made sense once I looked for that thing that I thought might be there, that, oh no, of course it's not going to be there, and this is actually much better.
Okay, we still have time.
Hi. I agree that the statistics you show may be a good indication of whether we have a good structure of our modules. And I was wondering if you have maybe an automated tool that can analyze the project and show us the statistics, because this would be helpful to analyze where we might have too much coupling and which modules might need to be refactored.
Mm-hmm. So it's not automated at the moment. Right now it's still a two-step process, but I do have that module dependency graph generator up on GitHub. If you want to use it for Elixir applications, it right now works on just about everything except like the Elixir code base itself and Ecto, because of some stuff that they do in the AST with playing around with it that right now it can't parse. Frankly, I haven't developed that any further because I wasn't sure if people would be interested in it. But right now, for simple Elixir applications, you can take that, run it on any set of files. It just reads the files and reads the ASTs of the files, and it will spit out a graph that you can put into that tool I mentioned, Gephi, or Jeffy, that you can find online, and that will do all the calculation for you, and you can dig into that dashboard that it shows you, and it'll show you which nodes have a very high clustering coefficient. You can take a look at just that part of your graph and see where the clustering is, and from that you can see if maybe there's something that you can extract, maybe there's a missing abstraction, maybe there's something that you could structure a little better there. So most of the hard stuff in terms of parsing the Elixir AST and giving us the module dependencies is up on GitHub if you want to see it.
Okay, any more questions? I have one or two comments actually. Yeah. So yeah, a few years ago I remember when Java and Maven dependency management was something new and cool, and then some of our students also did similar exercise as you with analyzing these dependency trees between different modules, and I think the results were quite similar. Yeah. So it's not exactly the small world network, and you mentioned also the trace, the messages between actors, for example, in a system. So just behind this wall, there was another talk. We heard some applause. Yeah. So my students have just presented a tool for tracing actor systems in Akka, and what they produce is actually a graph. Yeah.
Oh, nice.
Of these messages. So probably it's also an interesting option to feed this graph into one of the tools and see if there is there are some patterns.
Yeah, I'm sure the data's out there. If people have these huge applications that they're running in production and they have all that data. So if someone can get their hands on it and analyze it, that would be super cool.
Yeah. Oh, still there's some question up there.
It's not really a question, just a thought that I just had. So maybe in architecture of software, the thing that is both might be a sound design and a small world network, maybe layers of DSLs. So you decompose your problem into like layers of languages, and those are clustered together. Kinda. I mean, within itself, languages are clustered together, and they are also connected to the layer above and below. So. Yeah, just this. Have you encountered anything like that?
So what I saw most frequently was not that sort of layering, but those layers weren't necessarily connected. So for example, here You can see up in the top right there, I don't really know how this works. I don't use this type of thing before. But you can see up at the top right, those sort of sub-trees, and you can see another one at the bottom right there. Within those layers, there are lots of other leaves in that graph, in that tree, but frequently they weren't interconnected. They weren't calling each other. They were independent or calling something further down in the dependency graph.
Okay, thank you.
Hey, last question from the back.
When I was listening to your talk, I was thinking of torrent networks, specifically the Kademlia network for distributed hash tables. Have you done any research or looking into that? Because it seems like there's a lot of back propagation and similar systems to your small world network model.
I haven't done any research into that. I haven't thought about it, but now that you bring it up, that would be another great thing. I would be shocked if there were not small world networks in those sort of distributed file sharing, like an IPFS or something, like that sort of setup of distributed computing, distributed networking, distributed anything. These sorts of networks, I think, are going to be very common, although I have not looked into it at all. I haven't even looked to see if there's research on it or if people are consciously designing those systems as small world networks or not. But again, I would be very surprised if it wasn't there. It seems like a sort of natural fit based on what a small world network gives you and what they want out of that. So.